Okay, so let's begin. Um, so we will. So last time we were looking at localization. Before I begin, let me just tell you. So instead of this Friday, I'm thinking we will do the quiz on Tuesday, next week Tuesday, and then we will take a break. So there won't be any class on Thursday and Friday, and then we will reconvene after a week, yeah, following Tuesday. So that way we will end with a quiz. So we'll have a regular class this Friday, and then next week Tuesday we'll have a quiz, no class, and then we will have a mini break, and then we will start the following Tuesday lectures. Okay, is that fine? So if you have some opinion about it, you can email me. If you are okay with it, then that will be the schedule follow. Okay, so last time we were talking about localization. It's a way of making things invertible. So we are changing the ring a little bit and making certain elements of the ring invertible. That is what localization does. Yeah. So in particular, we'll get. So if R is an integral domain, we get field of fractions of R. So something in which every non-zero element will be invertible. So it will be bigger than R. So we are yet to define that, but as a sample or as an example, you can think of rationals. Yeah, rationals are field of fractions of integers. So every non-zero integer becomes invertible in rational numbers, and you have a inclusion map from integers to rationals. So so this localization is motivated by this construction. Yeah, so it mirrors that. So we defined it last time, and today we will discuss it and make it a little more transparent. We'll do some examples and so on. So the way to do it is we defined what. So the definition of multiplicative set is gone. Yeah, so recall, so that I haven't done in this recall. So recall that a subset S is called a multiplicative subset of a ring R. So here R will always be assumed to be commutative ring with unity if 1 belongs to S and if S is closed under multiplication. That means if X and Y belongs to S, then X times Y belongs to S. And we saw various examples of multiplicative subset in R. So we'll recall them today anyway when we are doing some examples. Okay, so now if we have a multiplicative subset of R and of a ring R, then we can define an equivalence relation on this Cartesian product S cross R, and this is so one should view. So this equivalence relation and this relation is defined by S1 R1 is said to be related to S2 R2 if S2 R1 minus S1 R2 is 0, more or less. So what you want is S times some, and this should be 0 for some S in this. Yeah? So if S consists of only non-zero divisors, this is equivalent to saying S2 R1 minus S1 R2 is 0 in R. Yeah. So let me so this is a relation, and this we last time saw was an equivalence relation. This is an equivalence relation. Okay, so this is what we saw. This is one of the things which we saw. And then we look at the equivalence classes. And equivalence classes of S comma R. I said we should think of them as R over S of fractions like this. Yeah? So this is the interpretation we want of. Elements of S will become inverted in the new ring, which we are trying to construct. Yeah, and the new ring, the underlying set for the new ring was equivalence classes with respect to this equivalence relation. Yeah. So the set of equivalence classes S cross R mod this tilde. So this is how we denote the set of for general equivalence class, but this set we will denote it by S inverse R. And then we defined the two binary operations on S inverse R. So the addition was defined like we do addition of fractions, and multiplication was defined again like we do multiplication of fractions. Yeah, so these are the two binary operators. And we showed that, there was a big proposition in which we showed that these two binary operators are indeed well defined. And then we showed that this S inverse R with respect to these two binary operators is indeed a ring. Yeah. So we skipped some parts. So for instance, I think we didn't show that this plus is associative or distributive law and so on. But you can check all that. Yeah. So some steps we skipped and some steps we did. And then we also defined, we also checked that this ring, this map, which sends R to R over 1, from R to S inverse R, is actually a ring homomorphism. And we saw that the 0 of S inverse R, so 0 in S inverse R is basically 0 over 1. And 1 of S inverse R is 1 over. Yeah. And in fact, you can check this is 0 over S for all S in S. Yeah. So 0 over 1 is same, the equivalence class of 0 over 1 is same as the equivalence class of 0 over S. So that you can just check by verifying that 0 over 1 and 0 over S satisfy the same equivalence relation. And similarly, you can check that 1 over 1, this equivalence class is same as S over S for all S in S. Yeah. So they give you the same equivalence class. Because the difference itself is 0. Here every term, in the first one, every term will be 0. Here the difference itself is 0. So you can take the multiplicative factor to be 1. Okay, so this is more or less where we stopped. We stopped at showing that this is indeed a ring, and phi is indeed a ring homomorphism. Yeah, so this is roughly where we stopped. So today we'll hopefully see some example. I hope this is visible. So let's see some examples first. Yeah. Okay. So so for instance, we saw one example. So so there are many examples, but let's just see the first motivating example. Yeah. So R, an integral domain, or maybe first even the basic one. So let's just take R to be Z and S to be a set of non-zero elements, Z minus 0. Yeah. So in this case, what do we get? Yeah. So so note that S consists of all non-zero elements. So what does this? So it says that our S cross R is basically AB. Maybe let me. Yeah. So I'll write it as SR. Yeah. SR, where S is non-zero and R could be anything. Yeah. So it's non-zero. SR, an element of R. Yeah. So this is what this S cross R will be, and equivalence relation is S comma R S1 comma R1 is equivalent to S2 comma R2 if so technically it says there exists S, so maybe I'll just write there exists S in S such that so maybe just write S in Z minus 0 such that S times R2 S1 S2 R1 minus S1 R2 is 0. So all these operations are in integers, yeah. But S is non-zero, so this is equivalent to saying S2 R1 minus S1 R2 is 0, yeah. Which is so yes, basically we are saying that which is equivalent to saying that S2 R1 is equal to S1 R2. So and remember the equivalence classes of this, we were going to denote it by fractions. So this tells us that R1 over S1, the equivalence class, is equal to R2 over S2 if and only if S2 R1 is equal to S1 R2. Yeah, and that is what rationals is all about. Yeah, so as rationals are such fractions where this agreement holds. Yeah, so so S inverse R is precisely Q. Okay, so that's the description of rationals with your the usual addition and multiplication. Yeah. So so this does achieve the stated goal. Yeah, and so more generally, more generally. So maybe let's call this a definition. If R is an integral domain, and S equals R minus 0, then the ring, so maybe there's something to observe. So maybe I'll say definition / proposition. Like then the ring S inverse R, which we observed is a commutative ring with unity, is a field. This field is denoted by, so there are many notations. So, frac R, or so I used to when I was learning commutative algebra, this course or whatever, this algebra, basic algebra, then it was denoted by this. So quotient field, the yeah, this has become out of fashion, but I still use it. And so more so is denoted by frac R. But I may use this one. It's denoted by and is called field of fractions. Okay, so field of fractions makes sense only when R is an integral domain. Okay, otherwise it doesn't make sense. Okay, so so we have seen more or less everything in this proposition. That is, we have seen that this is indeed a ring, and so the only thing we have to check, yeah, and field of fraction. Okay, so I have to. So maybe I should say something more. So some other characterizing property of field of fraction. Yeah. So moreover, so there are other ways of defining field of fraction. R is contained in frac R as subring. So maybe this can be thought of as full-fledged proposition then. And frac R is the smallest field containing R as a subring. Okay. So this is what. So another way of defining fraction field is for an integral domain is that it's a field containing that integral domain and is smallest among all fields containing that. That means, in other words, there is no small. There is no proper subfield of this field which contains R as an integral domain. That's the meaning of it's the smallest field containing R as a subfield. Okay, is that clear? Okay, so let's
Sir.
Yeah.
Shouldn't it be some subring that is isomorphic to R, not R itself? Because in frac R we're taking the equivalence classes.
Yeah, sure. So yeah, so so subring R, yeah. So maybe one if we want to distinguish it, then yeah, sure. So moreover, R's yeah. Yeah, so we'll identify the image. Yeah, so we so yeah, so this and this field is yeah. So ours yeah. So maybe yeah. So let's just put it this way. Is injective. So the natural map P, which we defined in the previous construction, is injective. And frac R is the smallest field containing, so containing a ring isomorphic to subring. Now this is going to be a bit of an issue. Yeah, so the second one, I'll have to phrase it properly if I want to do it in terms of isomorphism. Yeah. So frac R is the smallest field containing yeah, so maybe I'll phrase it differently. Injective and and if K is a field containing a subring isomorphic to R, then K contains a subring, let's say, yeah. So I don't know if this is a good idea, but you identify R in K, yeah. With you take the identification. That is the best way of thinking about it, yeah, rather than complicating your life with morphisms and stuff. Okay, so there is a natural map from R to frac R. You look at its image, and that's the way you think of it. So if K is a field containing R as a subring, yeah, so that means I mean so when you say R as a subring, it obviously means that that subring is isomorphic to R, yeah, and then then it must contain the field of fractions as well. Okay, so that is how you can phrase it. Okay, so the point that it is a natural map is what comes into play. Yeah. So at this level, you can just think think of containments as sets and not worry too much about. So there is an ambient guy, right? A field of fractions. So you can think of some subset which is same as R. But if things become too so if you're comparing between two different sets, then it's a problem. But within the same set, it's not a problem. Okay, so let's see a proof of this this proposition. Okay. So proof. So first we will show that frac R is indeed a field, and then we will show this what is called this. It's a special case of what is called universal property of localization. So let alpha be an element of S inverse R. So we want to show S inverse R is a field, yeah, which S inverse R, which is same as frac R. So let's let alpha be in S inverse R, alpha not equal to 0. Then we want to show that alpha not equal to 0 in S inverse R. Then we want to show that this is alpha is invertible. Yeah. So how does alpha look like? So alpha is going to look like some R over S, some equivalence class R over S, where R belongs to R and S belongs to S, which is same as R minus 0. Yeah. So S is some non-zero element of R. Yeah. Then of course, what is the and since alpha is not equal to 0 in S inverse R, and we saw that 0 over anything is 0. Yeah. So this was this observation: 0 over S is 0 in S inverse R. So that tells you that since alpha is not equal to 0 in S inverse R, implies R is not equal to 0. in this description. Yeah? So this implies um, S over R, the equivalence class S over R belongs to S inverse R. Yeah? Because R, so which implies R belongs to S. Yeah. So we can do this construction. S over R makes sense. Then S over R times R over S is indeed SR over SR by definition of multiplication in this ring. So now I've switched to ordinary. So do you want me to switch? So I've switched to ordinary multiplication instead of this multiplication. Yeah. This dot circle. So technically one should put dot circle, but or maybe let's just put dot circle for now. After this proposition, we'll change it to ordinary multiplication. Okay. So this tells you that this is one of S inverse R because both numerator and denominator are same. Yeah. So this we argued above that this is same as 1 over 1, which is 1 of S inverse R. Okay. So that tells you that hence S inverse R is a field. Now the other thing we want to show is that this is in some sense the smallest field containing R in any field. Yeah. So we want to show more over parts. So let K be a field. No, we have to show that this map is injective. Sorry. So the map R to S inverse R is injective as well. Yeah. So phi, recall, is a map from R to S inverse R, which sends R to R mod 1, R over 1. Yeah. So we want to show that phi is injective. So let's analyze what is the kernel of phi. So kernel of phi is R such that R over 1 is 0. And what is 0? So 0 in S inverse R. So is same as 0 over 1. Yeah. R an element of R. And this is what kernel of phi looks like. And what does this mean? This is R in R such that so these two are same if there exists so if there exists S in R minus 0, S in S, which is same as R minus 0, such that 1 dot R minus 1 dot 0 times S is 0 of R. Yeah. So not S inverse R, no, of R. So there are two rings floating around. So one has to be careful which ring you are in. Yeah. So there is 0 of R and there is 0 of S inverse R. But what is 1 times R is R, 1 times 0 is 0. The difference is R. So this is saying that the, R in R such that S times R is 0. But S is non-zero, yeah, and R is an integral. So S R is 0. S not equal to R, not equal, not non-zero in S in R. Yeah, but this is same as saying some S non-zero. Yeah, but S R is an integral domain. So no matter which S you take, this is same as saying that R in R such that R equals 0, which is 0. Yeah. So the only thing which can go to 0 in S inverse R is 0 under this map, which implies phi is injective. Yeah. So this map is a injective ring homomorphism. So we already saw it's a ring homomorphism. So it says that it's an injective ring homomorphism. We in fact saw that 1 goes to 1. Yeah. So R, you can think of it as a subring of S inverse R by identifying the image of this map with R. Yeah. Now, for the moreover part, so the other part of this moreover part, let K be a field, and R prime contained in K be a subring. So I'll not do this version. Yeah, so I'll just think of R as a subring of K. Yeah, so this is also okay. So instead of containing a subring isomorphic to R, containing R as a subring. Yeah, containing subring R. So containing R as a subring. As a subring. Then K contains frac R prime is what we would do. Yeah. Let K be a field, R contained in K be a subfield, be a subring. Then we want to say that S inverse R is also contained in there. So let R over S be an element of S inverse R. Yeah. Then yeah, so I don't know, this looks like a tautology. Then yeah, so okay, I think it will make more sense if I do the universal property, and then yeah, then it will be a little more formal. Yeah. Okay, so I'll just write it this way, and so this is a special case. So when we do the map version, we will see in a more reasonable way. Yeah. So let's take R over S. So R over S. Yeah. So yeah. So the right way to say is that there is an injective map from S inverse R to. So if there is an injective map from R to K, then there is a injective map from S inverse R to K, which makes the diagram commute. Yeah. So that's the right way. So we'll do that when we are doing the this universal property. So far I'll do it a bit. I'll write it in a bit vague way. Yeah. So R over S belongs to S inverse R. Then of course, S is not equal to 0 in R, and R belongs to R implies R over S is an element of K. Yeah. So S inverse R is contained in K. Yeah, so given any element of S inverse R, I've showed it in, but somehow the way we have constructed S inverse R is some equivalence class and so on. So one should give a map speaking completely rigorously, yeah, because S inverse R may not. So one should give an injective map, but sort of with respect to some identification, this is okay. So that completes the proof. So if it bothers you in some way, then you can look at the next. So we'll do universal property, and there it will become more clear. Okay, any questions? Okay. Okay, so if there are no questions, so this was the definition of field of fraction. Now what we want to do is analyze this this localization a little bit in more examples. Yeah. So before I go to the universal property. Yeah. So it's so this map phi need not always be injective. First thing. Yeah. So for instance, um, um, or even before that, so I told you that this is a way of constructing a ring where elements of S becomes invertible. Yeah, so maybe this is the first observation I should make. Start doing this. More examples. Let's just do this observation first. Yeah. So you can call it a proposition as well. So so we are in the same setup. So let R be a commutative ring with unity and as multiplicative subset of R. Okay. Subset of R. Then phi S is a unit in S inverse R for all S in S. Here phi is the natural map. Phi from R to S inverse R is the natural map. Natural map meaning R going to R over 1. Yeah. So this ring of homomorphism. Okay, so that tells you that every element of S becomes sort of invertible in this ring. Yeah. And this is straightforward. So so we want to show that phi S is a unit in S inverse R. So you just look at phi S. What is phi S? Phi S is S over 1. Is an element of S inverse R. Of course, so S belongs to S. So we 1 over S also belongs to S inverse R. Yeah, because we can put so equivalence class of 1 comma S is there, and equivalence class of S comma 1 is also there because S belongs to R. Yeah. So S1 over S belongs to this. Hence, and so it's just one line. S over 1 times 1 over S is equal to S over S in which is equal to 1 over 1, which is equal to 1 of S inverse R. Hence, phi S is a unit. Okay, so it does the job. It converts every element of S into a unit. Yeah. Now, of course, so this will become a problem. I mean, this will become a problem if S contains 0. Yeah. So if 0 belongs to S, then of course we are inverting 0. So then something is a problem. Yeah. So then we should get something weird. So what can you say about S inverse R if S contains 0?
Only one element.
Yeah, so you want 0 to become invertible, yeah, and we know only one ring which has 0 invertible, and that is the 0 ring. Yeah, so is the 0 ring. And the ring with one element, which is the 0 ring. Okay, so again, this is sort of straightforward. So if 0 belongs to, so you just take any element R over S. Yeah. So what we want to show is claim R over S equals 0 over 1 for all R in R and S in S. So if we show this, then that's it, right? So that will tell you that S inverse R is the 0 ring. And the way to see it is, it's just this equality. So the equality, the above equality holds. Equality holds. So by definition, if 1 times R minus S times 0 times U equals 0 for some U in S. And this 0 is, so all the zeros here is in the ring R. Yeah. So this identity should hold for some U in S. And of course, take U to be 0 because that belongs to S, and hence the claim. Yeah. S inverse R is the 0 ring. Okay, so that's the reason. So last time when we were discussing various multiplicative subset, I told you that we shouldn't look at sets which contains 0, yeah, because as soon as S contains 0, the localization doesn't give us anything interesting. Secondly, so other extreme case was when S contains units, yeah. So so maybe these are all. So I'm giving you some instances of the universal property. So maybe, or maybe this one I'll prove using the. So what we'll show is that if S contains units, then what can you say about S inverse R? Any guesses? So R is a commutative ring with unity, and S contains contains only units of R. So it's a multiplicative set containing some subsets of units of R. Then what can you say about S inverse R?
We won't gain anything.
Yeah, go ahead. One person maybe who hasn't spoken. What do you get?
It'll just be R.
Yeah, so you'll get R itself. Yeah, so or more formally, this phi, this map phi will be a isomorphism. This natural map from R to S inverse R will actually be an isomorphism. Okay. So we'll see that using the universal property. I should keep something for the universal property. Yeah? And but one observation I want to make is that so you see in this case, of course, phi is not an injective map, right? In this case, when S contains 0, then no matter which ring you took, everything, the whole ring is in the kernel. Yeah. So phi is far from an isomorphism. So in general, it's a good idea to know what the kernel of this map is. Yeah. So in general, as multiplicative subset of commutative ring with unity R, then and phi is this map. So phi and phi from R to S inverse R is the natural map. I'm going to R over 1. Then kernel of phi, maybe I should write it in the next line. Then kernel of phi is, so what will it be? So it's, so we wrote down some description here, so I can just copy this description. Huh? So so it's R in R such that S times R equals 0 for some S in S. Okay. So in particular, if S consists of only non-zero divisors, then phi is injective. Yeah. In particular, if S consists of non-zero divisors, in R, then so meaning it need not contain all the non-zeros. So every element of S is a non-zero divisor. In R, then phi is injective. Yeah, because if S consists of only non-zero divisors, then S times R equals 0 for some S in S means R must be 0. So that tells you that the kernel of this map is 0. So it's injective. But as soon as S contains a zero divisor, then of course kernel phi is non-zero. Yeah, so you even have a converse, because if S contains a zero divisor, then you take R to be an element such that S times R to be a non-zero element such that S times R is 0. Then that element R will be in the kernel. Yeah, so this is if and only if. Yeah, converse also holds. Okay. So I suppose this is so I don't have to prove this, yeah, because this description we already saw. Yeah, kernel of phi is this guy. Now you can copy these 3 steps here. Kernel of phi is R such that R over 1 is 0 over 1, which is same as saying R in R such that there exists S such that S times 1 times R minus 1 times 0 is 0, which is same as saying S times R is 0. So the same proof works here. Okay. Okay, so maybe next will be the universal property. So maybe let's take a break now of 5 minutes, and then we will do the universal property of localization, and then maybe do a few more examples. Okay. So let's reconvene at let me see, what time is it? Yeah, so 12. So let's reconvene at 12:05 or 12:06. Resume. Okay. So are there any questions before we resume? Okay. Can you all hear me? Let me just check. Recording is on. Yeah. Okay. So let's resume. So next thing is the universal property of S inverse R. So like if you have R a ring and I an ideal, then quotient has some sort of universal property that any ring in which any ring homomorphism from R to say R prime such that I is in the kernel, you get a map from R mod I to that ring. Yeah, this is given by the first isomorphism theorem. So similarly, remember quotient also comes, this quotient ring R mod I also comes with a natural map Q from R to R mod I. So in the same spirit, this S inverse R has a universal property which I'll write. And remember, it also comes with a natural map from R to S inverse R. Yeah. So let maybe I have to write a little thing. So theorem. This is called the universal property of localization. Okay, so let R be a commutative ring with unity. S contained in R be a multiplicative subset of R. Let F from R to some other ring, let's call it A, be a ring homomorphism where A is a commutative ring with unity. Then we want to say that this map and such that. So remember, what is one important property of this this localization? It sends every element of S to make it into a unit. Yeah. So such that Fs is a unit in this in ring A. Yeah. And then what you can say is that there exists a map from S inverse R to A, which will make this diagram commutative. Then there exists, in fact, there exists a unique map, unique ring homomorphism. So this map is a ring homomorphism. F tilde from S inverse R to A, such that you first apply first apply phi, which is a map from R to S inverse R, yeah, and then apply F tilde. So you get a map from R to A. This is same as F, yeah, pictorially. So you have R to S inverse R. This is your given map phi, and you have a map here F. Then what it says is there exists a unique map F tilde, which will make this diagram commute. So you go this way or that way, you get the same thing. Okay, so this is the statement of the universal property of localization, and we'll prove this. Yeah? So one can define S inverse R in some different way using this universal property. So I'll talk about that as well if time permits today. Otherwise on Thursday. Yeah. Okay, I didn't want to do this. Yeah. Okay. So what is the proof? So
Excuse me, sir.
say that again.
So excuse me, sir. Over here, what exactly is S? Is it all S belonging to S? Fs is a unit in A.
Yeah. For all S, such that for all S in S, Fs is a unit. This is what I meant. Yeah, good point.
Thank you.
Yeah. So every element of S becomes a unit. So that's what the hypothesis is. Yeah, Fs is a unit for all S in S. Okay, so let's try to prove this. So we want to prove. So we want to construct this. So the proof basically means that we have to construct this F tilde, and we'll have to show that it's unique. Yeah. So let's define F tilde. So F tilde from S inverse R to A. Yeah. So how do we define this map? So we'll have to take an element here. Yeah. So let R over S be an element of S inverse R for some R in R and S in S. Yeah. So what should be F tilde of R over S? So we should get some element of A. Yeah. So to define something, we'll need F. Yeah. So it should go to FR times Fs inverse. Yeah. So this is F over Fs somehow. So to behave in a reasonable way. But over Fs makes sense. The point is, Fs is indeed a unit. That is what we are assuming in it. Yeah. So this makes sense. So the where. So maybe I should say instead of where, note Fs is a unit in A, hence Fs inverse makes sense. So you can define it this way, but there is still a problem. Yeah, the problem is we are defining it a map on the equivalence class by using its representative. Yeah, we are using R and S, the representative. We are using R and S, which are representative of this thing. Give me a second. Yeah, I'll be back. 1 second. Okay, sorry about that. Yeah, so F tilde R over S is Fs inverse times Fr. And the point is we are defining it using representatives. Yeah, so we will have to check that it's well defined. Because if we take a different representative, we get the same thing. Yeah, so we have to check F tilde is well defined, and then the rest of the thing is straightforward. Even checking well defined is not difficult. Yeah. So let R prime S prime be equal to R over S. So what maybe I should say F tilde is well defined is what we are checking. Is well defined. Well defined. This implies there exists u in S such that u times SR prime equals minus S prime R equals 0 in R. So this is what the two equivalence class being same means. And that means these two belong to the same equivalence class. So now we want to show that so this implies if this is 0, then what does that mean? That means fu, so you just apply f to this equation, fu times fs fr prime minus fs prime fr is 0 in A. Yeah. So since we are using the same 0, I'm just writing where we are working. Yeah. So and this is just because f is a ring homomorphism. Yeah. So you can distribute it. You apply f, you get this thing. So f is a ring homomorphism. Yeah. And this implies, so remember fu is a unit because since u belongs to S and every element of this goes to a unit. Yeah. So this implies so fu is a unit, in particular non-zero divisor. So this tells you that fs fr prime minus this guy is 0, which is same as saying fs fr prime equals fs prime fr in A. So now of course everything is in A, so this in A is useless, but anyway. And then again fs and fs prime are invertible, so we can multiply by fs inverse fs prime inverse, this equation, multiply by this, and we get that fs prime inverse fr prime is equal to fs inverse fr. Yeah. Hence and this is so that tells you that this was the definition of f tilde r prime over s prime, and this was how we intended to define fr over s. So meaning on the on equivalent elements we give the equivalent on equivalent classes we get the same definition. Hence f tilde is well defined. Yeah. So this is how we conclude that f tilde is well defined. Now finally we want to check that the other property hold, so that it's unique and the diagram is commutative. So let's just check the diagram commutes. So we also have to check f tilde is a ring homomorphism. Sorry. So f tilde of r over s plus r prime over s prime. So we want to show it same as f tilde of r over s times f tilde of r over r prime over s prime, and same with multiplication. So I'll check with addition, and multiplication should be similar. Yeah, should be simpler in fact. So what is this? So this is f tilde of so by definition of this sum, this is s prime. So I'll not use this complicated plus because we are not doing it consistently. So let me just write it this way. Yeah, s prime r plus s r prime, which by definition is f s s prime inverse, and what we get here times f of s prime r plus s r prime. Yeah, so that is the definition of f tilde. If you are given a fraction, then this is what you do. You take f of denominator, take its inverse, and then f times the f of numerator. And this is by definition, this is same because f is a ring homomorphism. This is fs inverse, fs prime inverse, and the left hand side becomes and the remaining term becomes f of s prime f of r plus f of s f of r prime. And then if you multiply this through, what you get is f of, so this f of s inverse and f of s prime inverse and f of s prime cancels out. So what you get is f s inverse f of r plus f of s prime inverse f of r prime, which is f tilde of r over s plus f tilde of r prime over s prime. Similarly, so I'll just say similarly f tilde of r over s times r prime over s prime, you can check, is f tilde of. So this is more straightforward because multiplication in this ring of fractions is straightforward. Yeah, times f tilde of r prime over s prime. Okay, so f tilde is indeed a ring homomorphism, and then we check the remaining properties. So f tilde composed phi evaluated at r for r in r. So here I should have done for r over s and r prime over s prime in s inverse r. We get this. And similarly for r in r, any arbitrary r in r, phi tilde composed f tilde composed phi of r, same as f tilde of r over 1, which is same as f1. Remember, f is a ring homomorphism, which takes so I mean these are all commutative ring with unity, so one has to go to 1. Yeah, so if it is f1 inverse f of r, which is so since this goes to 1 of a, so this is same as f of r. Yeah. So this implies that f tilde composed phi is equal to f. Okay. Any questions? So that completes the, oh, so one more thing we have to check, that f tilde is indeed unique. Yeah. So, and that will be all. Yeah. So finally, f tilde is unique. So meaning there is no other map like this which will make this diagram commutative. No ring homomorphism which will make this diagram commutative. So that let's say H from S inverse R to A be another ring homomorphism. Yeah, such that H composed phi is equal to F, then we want to say that H is same as F tilde. Yeah. Then we want to say H and F tilde agree. So let's take any element. So let R over S be an element of S inverse R. Yeah. Then what is then note that H of yeah, so how do I show this? Yeah, so consider H of R over S. Yeah, we want to show that H of R over S is same as so H of R over S is same as is some element in A. Yeah. So yeah, so I can write it as H of S inverse times H of S. Maybe I should write it this way: H of S inverse, H of S over 1. Yeah, so so the right way to do it is not this, but do it this way. So note R over S is same as R over 1 times 1 over S. Yeah, in the ring of fractions. So this is same as H of R over 1 times H of 1 over S. Yeah, but this is equal to, what is H of R over 1? This is H composed phi of R. Yeah, because phi of R is R over 1. And what is H of 1 over S? So H of 1 over S is going to be some element of A, but this you can also think of it as H of S over 1 inverse. Yeah, so remember 1 over S is same as inverse of is inverse of S over 1. Yeah, and in ring homomorphism, if U is an element of R, which is a unit, and then HU will go, HU inverse will go to HU inverse of HU. Yeah, so that is what we are using, which is again same as H composed phi of R. So H composed phi is F. So let me just write this as F of R times H. So this is H composed phi of S inverse. So this is same as F of R, F of S inverse, which was the definition of F tilde. Just that we wrote Fs inverse here. Okay, so this implies H is equal to F tilde. So now our proof is complete. So now we have shown that F tilde is also unique. Okay, so there is no time to tell you how this would imply this thing. How this will, I was going to tell you something. Yeah, for instance, how this will give you some isomorphism when S consists of units, and something more. So about field of fraction, you'll use this description to make it more precise. Okay, so we'll stop here, but next time we will see this universal property more carefully and see some applications of that. Are there any questions? Okay, so if there are no questions, we'll meet on Thursday.